So a guitar string is fixed at the bridge, and then again at the other end when it runs over the nut. At least I'm told that's the nut, and I have no reason to distrust my friends. So have a guitar string that's fixed there and fixed there, then these points must be equivalent to these nodes. So there could be two nodes that are next to each other like that, or they could be two nodes that are some distance away. And what that means is that the standing wave has to look like one of these. Maybe it look like that, or alternatively it could look like the next one that has a node in the middle, where these things are just going up and down, or the obvious ones with higher numbers of nodes. Now this one here is called the fundamental, and the higher order ones are called the harmonics. And sometimes the fundamental is called the first harmonic, and then this one would be the second harmonic, and therefore that would be the third, and that would be the fourth. But some people label them differently. They say, no, the fundamental is special, and then this would be the first harmonic, and then this one would be the second harmonic, and so forth. So it doesn't matter what we call them, we know what they are. Now, these things sound different. Why do they sound different? They sound different because in order to make this wave here, in order to have that wavelength, and because the speed of the wave in that string is set by the string, how tight it is and how heavy it is, that means it's got a very particular frequency. And remember, different sounds come with different frequencies. So this string is going to drive the air at a particular frequency, and that's going to make a sound of a particular frequency. And so what frequency is it going to be? Well, what's the wavelength? Remembering that the wave here, a full wave, goes like that, and then comes back, and then it repeats again. And so that would be the full wavelength. This distance here would be the full wavelength. So that would be the wavelength. And so this part here is, of course, just half the wavelength. So the length of that string is going to be half the wavelength. In this case, the length of the string is precisely one wavelength. In this case, we have one wavelength there, and then another half. And then we have two full wavelengths, and so on. So you'll see for each of the higher harmonics, the wavelength is getting shorter and shorter and shorter. So here, the wavelength is twice the distance between our bridge and our nut. Here, it's exactly the distance between our bridge and our nut. And then it's 2/3, and then it's a half, and so on. So as we said, the speed of a wave, and remember we normally call the speed c, the speed of a wave in a guitar string is basically only dependent on how tight the string is and how heavy the string is. And so as we change the wavelength, we're going to change the frequency, because the speed, remember, is related to the frequency and the wavelength. So it's just the frequency times the wavelength. In other words, it's how far you travel per cycle divided by how fast you do it, which is one period. And the frequency is 1 on the period. So if we rearrange that to find the frequency, it's just c on lambda. So as you make the wavelength smaller and smaller, you make the frequency higher and higher.